In this video, we're going to learn how to determine the domain of a logarithmic function. Now, y is equal to log base b of x. Its defining equation is b to the y power is equal to x. So since this exponential b to the y expression can only produce positive numbers, it makes sense that x needs to be a positive number affecting the domain of a logarithmic function to only be numbers x that are greater than 0. So to determine the domain of a logarithmic function, we essentially just take what the inside part of the logarithm is and have it be greater than 0, and then we solve that inequality. Now, solving this inequality, we just have to subtract 3, so we get x is greater than 3. So the domain of our function would be all numbers x such that x is greater than negative 3. Or if you want to use interval notation, that would be negative 3 to infinity. Now, sometimes the inside of your logarithm could involve another type of function. So in this case, the inside of this logarithm is absolute value of x. So we're looking for where is absolute value of x greater than 0. Well, hopefully it's always greater than 0 because it should always represent a positive number. But there is one spot where it can't be, where we have one x value that cannot be used because we don't equal 0. So I can't actually plug in 0, but any negative number I would plug in or any positive number I would plug in would be fine. But when I plug in 0, it does not work. So I know that x cannot equal 0. So my domain is all numbers x such that x does not equal 0. Or in interval notation, that would be negative infinity to 0, union 0 to infinity. Let's see if we have a quadratic equation inside of a logarithm. Well, we see to know when is x squared plus x minus 6 greater than 0. Now we have a polynomial inequality. So to solve this, I need to factor, giving me x plus 3 times x minus 2 is greater than 0. From here, I will make a number line to organize this information. Anything that would make this polynomial 0, I will label on the number line. So that would be negative 3 and 2. So splitting up the entire number line from negative infinity to positive infinity, I have 3 intervals. Now, whichever intervals cause this polynomial to be greater than 0, I will use for my domain, and those that make it less than 0, I will not use. Now, even though negative 3 and 2 make the polynomial 0, since it doesn't equal 0, these will not be used in the domain. So I will pick a number on each interval. So I'll use negative 4 on the first one, 0 on the second interval, and 3 on the last one, and plug all 3 of these numbers into this polynomial, which I'll call f. So look for f of 4, f of 0, and f of 3. When I plug in negative 4, I get negative 4 plus 3, which is negative 1, times negative 4 minus 2, negative 6, which is a positive 6. Since I had a positive number here, this means that this value is positive for the entire interval, meaning it's above the x-axis, which is what I'm looking for. So that will be part of my domain, negative infinity to negative 3. When I plug in 0, I get 3 times negative 2, which is negative 6. That would make it below the x-axis. So that would make it negative, which is not greater than 0. So I will not use that on my domain. And lastly, I have f of 3. When plugged in, gives me 6 times 1, which is positive 6 again. And that, since it's positive, puts it above the x-axis, which means I will use that interval. So my domain is negative infinity to negative 3, union 2 to infinity, leaving out that middle interval. The way I can write this in set notation is all numbers x such that x is less than -3 or x is greater than 2. Now for the last example, I have a rational function within the logarithmic function. So I'm looking to see where is 1 plus x over 1 minus x greater than 0. Now, luckily this is already factored, so I can jump right to that next step to see where it's positive and where it's negative. So I'll draw a number line for a graphic organizer. Now, -1 would make my numerator 0. So that's where my rational function is 0. And +1 makes my rational function undefined. So I'll label those 2 points on my number line, and then everywhere else should either be positive or negative. So splitting up my intervals, I have -infinity to -1, -1 to 1, and 1 to infinity. And now we're going to search for where is it positive and negative by picking numbers within each of those intervals and plugging them into the function, which I'll call, since it's a rational function, r. So r of -2, r of 0, and r of 2. When I plug in -2, I get 1 plus -2, which is -1, over 1 minus -2, which is +3. So that's -1/3, which is negative, so that puts it below the x-axis. So I don't want to use that for my domain. Plug it in 0, I get 1 over 1, which is 1, which is good. That's positive. That makes that above the x-axis, which I want on my domain. So -1 to 1 will be on my domain. Plug it in 2, I get 3 over -1. -3, that's negative. That puts it below the x-axis, so I do not want to use that interval. So I have a very small interval of numbers I can actually use for this logarithm. Its domain is much smaller than the previous examples. In set notation, this would be all numbers x such that x is between -1 and 1. And that is how you determine the domain of a logarithmic function.